All right, how's everybody doing today? It's Friday, and I'm in a relatively good mood, so to celebrate, we'll pass the candy. All right, so moving forward here, system partition function, molecular partition function, we've talked about the connection between the two, and we've been discussing how we get at molecular partition functions. All right, something I wanted to emphasize at this point, and this is going to be important, this showed up actually in the homework that was due today. So whenever you're calculating the partition function, and you have these, if you're doing it using the series, those terms that become really, really small basically mean there's a really low probability of being in a particular state. And therefore, they contribute not very much with regards to the total partition function. All right? And so what one can conclude from that is that if you have little to no probability of being in a particular state, you don't need to worry about that term. And that becomes important when we talk about electronic partition functions, right? All right, and then, this also goes with the temperature. So if the temperature goes up, you get higher probabilities of occupying additional states. Hopefully, some of the exercises that we've done with Boltzmann factor have cemented that. And at low temperatures, you coalesce in the lowest energy states. And you have little probability of being in higher energy states. So last time we met, we talked about the Maclaurin series. We showed where this came from. We've pointed out in order for the series that we calculate to work, we need to use the ratio test because we want to make sure that things converge. From there, we started our derivations of analytic expressions for the molecular partition functions. So we started with monoatomic ideal gases. The atomic energy can be described as consisting of translational and electronic. And because of the property of partition functions being associated with the summation of exponentials, we know that the molecular partition function is the product of the individual partition functions. All right, and then we went immediately into looking at the translational partition function, starting back with our particle in the box energy levels. And basically what we showed was that our summation over nx, ny, and z is three different summations that are equivalent, right? And therefore we could look at one summation from n equals 1 to infinity, and we cube it, and we've got the partition function, all right? And then we said, well, we don't really want to deal with series if we can help it. So if this is a really small number, I can replace the summation with an integral. All right, and so then from there we basically derived what we've been using for the partition function for translations. And because the translation is energies refer to the motion of the center of mass, what we've derived works for a monoatomic ideal gas, but it works for any ideal gas when we're talking about a translational energy, because in every case we're talking about the center of mass moving through space. All right, and then we're going to talk, we didn't quite get there last time on this, so we're going to pick up at this point. But basically, once we have Q, we can calculate the average energy of the particle, and then we can use that to calculate the energy of our system. All right? Okay, so some things that we're going to do today is we're going to extend our discussion to diatomic molecules. So again, what we're going to do is we're going to start with the partition function. That means we need to know what the energy levels that are available to our particles. So we're going to talk about vibrations. So back in chapter 1, we introduced the idea that our vibrational energy levels are given by this equation. This is using the harmonic oscillator model. And then we're going to talk about rotational energies and use those to determine an expression for partition function. We probably won't get there quite today, but it doesn't hurt for us to talk about where we're going to start. And this refers to the energies levels for rotations. Right? So where we're going to go today, the electronic partition function for a monoatomic ideal gas. Some of the homework that was due today, the one where you calculate the probability of being in a particular electronic state, leads right into this. So that was by design, believe it or not. All right, so, and then what we're going to do sort of like a little global overview. We're going to go through it before, because everything that we're talking about with regards to the calculation of energy of our system, the heat capacity and pressure, we've done before, all right? But because it's important and because we'll repeat it, all right? And then we're going to go on to our diatomic molecules, okay? All right. And then in order to talk about the diatomic molecules, we need to define our energy zeros. Again, we've done this previously, so this is going to be a review. We're also going to introduce something called a vibrational temperature. And because this can be a little bit of confusing, I think I want to start by talking about the vibrational temperature. All right. So what we know is that h nu V plus 1/2 is equal to the energy of vibration, right? Okay. And we also know that our Boltzmann factor is e to the minus beta times the energy, if we're talking about the vibration, right? And that in turn is equal to minus e vibration over kBt, okay? And when we put this vibrational energies in here, we're going to have an h nu term in there, all right? So we've got a lot of variables that we're tossing around. So to reduce the number of variables, we're just going to introduce this capital theta, VIB, all right? That's called the vibrational temperature, and it is defined as h nu over kb, okay? All right, and so whenever you think about putting h nu in here over kb, that means this is going to simplify this expression, okay? Now before we move forward though, I do want to point out that this, so h is clearly a constant, k is a constant, and then nu comes from spectroscopy, right? So because we're talking about vibrations, what kind of spectroscopy is it, or what portion of the electromagnetic spectrum? It's the infrared. All right, so from vibrational IR spectroscopy, right? And that also says that we can get these vibrational temperatures from the vibrational spectra, right? It's just a hop, skip, and a jump from the frequency. Does that make sense, everybody? All right, so theta vib is from vibrational infrared spectroscopy as well. Okay, so where we were last time, this is where I'm going to go back to my notes, make sure that I'm not going to lie to you, at least on purpose. Okay. All right, so we've determined that our translational partition function is given by this analytic expression, all right? And then I just wanted to point out, we know that we can take the derivative of the natural log of this with respect to t or with respect to beta, and that will help us get the energy of the system. I also can take the derivative of the natural log of the volume, and we know that that gets us to the pressure. Right? So it's nice to just note that this Q is a function of the temperature times the volume. Right? That just makes some of the math easier down the road. Okay? All right, and from there, I'm going to do something that we've done previously, so I'm going to try to go through it pretty quickly. We know that the energy of our particle on average, or our average particle energy, is given by kBt squared partial natural log of Q translation with respect to t. So that's going to be the same as kpt squared. All right, we're going to take the derivative with respect to temperature. We're going to be holding the volume constant. All right. So again, what we've done previously is we look at our partition function. We see we're taking the derivative with respect to t. So I'm going to tease out that portion of it. So it's going to be the natural log of t to the 3/2 plus the natural log of everything else, 2 pi m kb over h squared, that quantity, to the 3/2 times the volume, all right? And then all we need to do is take the derivatives. What's the derivative of this portion with respect to t? That goes to 0, all right? So we'll just say d dt equals 0. All right, and that means I really need to only worry about this front end of this. So I've got kb t squared. All right, so I've got the natural log of t to the 3 halves. I can write that as 3 times natural log of t. So I can pull that out in front. I mean, at this point, I'm thinking that most of you guys can do this in your sleep. What's the derivative of the natural log of t with respect to t? 1 over t. All right, and that comes out to 3 halves kb t. Okay, which again we've seen before. So this is our translational energy of average translational energy of a particle. Right. If I want to know the system, I multiply that by. Well, if I have 2 particles in the system, what am I going to multiply this by? Okay, all right, so we multiply it by the number of particles, right? Because we didn't get an immediate answer on that, let me just go ahead and say energy transition or translation would be given by 3 halves n kb t. Okay? All right, so next up what we want to do is talk about electronic partition function. So this will be Q electronic, right? And we just want to remind ourselves we're talking about atoms and ideal gases. Okay? All right, so for the electronic partition function, we're going to be thinking of this as a summation, but we're going to do it in terms of levels. All right? So we're going to say from I over levels. All right? I know I'm going to include my Boltzmann factor, so this would be e to the minus beta, e, and I'm going to do ei. That just says we're referring to the electronic energy, and that's the ith level. Right? What else do I need to include if I'm talking about levels? So if I'm doing quantum states, it's simply the summation of the Boltzmann factor over all the states. But if I have levels, I know I can have 2 states or more states in the same energy. So what do we call that? Degeneracy. The degeneracy. Okay? I feel like we're playing charades today. Gee, I know it's Friday. Okay? All right, so we're going to skip this little line. All right? You may recall that whenever we've talked about electronic energies for single atoms, we've defined the ground state as being 0 with respect to energy. So we can say E, I, and that should be a 1 in there, is going to be 0. All right? So when I go to do my summation then, that means this is going to be e to the 0, which is 1. All right? So my first term is simply going to be the degeneracy of the ground state, so GE1. All right? And I'm going to put in parentheses here, this is e to the minus 0 is the Boltzmann factor. All right? And then from there, I just write the rest of the series. So plus GE2 e to the minus beta, e for the first excited level, all right? And then plus GE3, e to the minus beta, E3. Okay? All right, what we're going to see momentarily is that this term's usually the only one that's important. And in the homework that you turned in today, that was due today, you showed explicitly that when you calculated the partition function, that dominated for the atom that you looked at, right? I forgot what the value of it was. Was it 2? I think it was 2, right? And everything else was smaller. So there are some exceptions. We'll talk about those very briefly, and those are halogen atoms. Okay? All right, so we can say that this is true in general by using a back-of-the-envelope calculation. So I'm going to do the back-of-the-envelope calculation in a moment. What I want to do is just look at some experimental data. All right? So in every case, we've defined the ground state. So hydrogen, helium, lithium, fluorine. Ground state is 0. All right? And then from spectroscopy, we look at the excited states, and we see that this is on the order of 10 to the 5th wave numbers. All right? I come to helium. It's also on the order of 10 to the 5th wave numbers. And then we come to lithium. It's on the order of 10 to the 4th wave numbers. Okay? All right. And then remember I said that we have exceptions for halogens. We see fluorine's got one low-lying level. All right? And we'll do a calculation about that in a little bit. Okay? But so what we can say in general is most of these electronic transitions have an energy of 10 to the 4th wave numbers or greater. All right? And so what we can do is we can calculate a generic Boltzmann factor using that energy. All right? So looking at that, we can say beta times the energy is going to be the same as the energy over kBT. All right? We're going to say this is, in general, 10 to the 4th wave numbers. All right? All right. Over kb, we know that kb is 1. I'm going to simplify this because this is an approximation. 1.4 times 10 to the minus 23 joules per K. All right? Then we have to do a conversion because we've got two different energy units here, wave numbers and joules. All right? And again, I'm using an approximation. One wave number is on the order of 2 times 10 to the minus 23 joules. Okay? All right, so 10 to the 23, 10 to the 23 cancel. We've got, roughly 2 over 1 times 10 to the 4th. So we can say it's around 10 to the 4th. All right? I forgot my 1 over t. All right, so we do the back of the envelope calculation. That comes out to 10 to the 4th. Units will be Kelvin and then times 1 over t. Okay? Does everything I did there make sense? All right? And the unit, that's because I had reciprocal Kelvin down in the denominator. So that gives me Kelvin in the numerator. And when we put in an actual temperature, that's going to end up canceling. All right? So if I talk about looking at 300 Kelvin, this is going to become e to the minus 10 to the 4th K over our temperature, 300 K. All right? And that's e to the minus 33. And that comes out to be on the order of 10 to the minus 15. Okay? All right, so let's go ahead and look at what that means. Okay? So this says, in general, this term is 10 to the minus 15th. This term is 10 to the minus 15th. The degeneracies are integers, right? So 1, 2, 3, 4, that kind of thing. Right? So that means this is going to be 4 times 10 to the minus 15th. This is an integer. 1, 2, 4, 6, right? Insignificant, insignificant. Does that make sense? All right, 300 Kelvin, that's room temperature. If we do the same calculation at 1000 K, this comes out to be on the order of 10 to the minus 5th. All right? And so what we can say is that for most atoms, if they're not halogens, the atoms are going to have only the degeneracy as their partition function. Okay? The degeneracy of the ground state. All right, well, let's go ahead and take a moment to look at the fluorine. All right, and we can go through this pretty quickly because I've done all the calculations. So I'm asking the question, well, what's the fraction that are in that lowest lying excited state? So the fraction in E2, right? So that's going to be e to the minus beta E2 times the degeneracy of E2, and that needs to be divided by our partition function. Okay? All right, so again, we've seen this before. For this particular example, that the numerator is calculated here. We see that it comes out to be 1.18 or 118, all right? And then our denominator, the partition function, will be the summation of the first few terms, right? So here's the degeneracy of the ground state, so that's contributing 4 to the partition function. That next term we've determined is 1.118, and then the next term we see is incredibly small. All right, so it means we don't have to worry about adding that in there. I mean, you can, but it's like adding 0 at something, right? Okay, so that denominator becomes 4 plus 1.118, and that comes out to be 0.22 approximately, right? So this says that if we're at, where are we looking at? So this is 1,000 Kelvin, all right? And at 1,000 Kelvin, we find that about 22% of the molecules are in the, or the atoms are in the excited state, right? And this is an exception, right, because it's a halogen. All right, if I do the same thing at room temperature, as one expects, you lower the temperature, you decrease the probability of being in an excited state, so it goes down to 7% roughly. And then if I go to a higher temperature, as we expect, we see that we increase the population of the excited states. Okay? All right, so basically I hope that we've shown that for translational energies for atoms, the first two terms are sufficient. Okay? All right, because I've been doing a lot of talking and because it's Friday, I have a gift for you. All right. All right. And this is very similar to what you guys working as a team? Yeah. All right, it looks like you guys have a little bit over 4, so we'll give you 2. You guys one team? Whoa. One team? Strong team. One team? All right. Sure. There you go. Whoops. All right, and this one I actually want you guys to work on your own. I will put the answer up later because we've gone through this kind of thing completely. So you're going to be awarded part credit for getting the correct answer. Okay? And did the candy box get around the room? Okay. You're using an Excel spreadsheet to calculate this? Is that right?
We're just going back to the...
Oh, the homework. All right. I take it back. Oh, that's all right. Now I feel bad. So if you establish that a Boltzmann factor is too small to be significant, guess what you can do with it? Assume it's 0. Yeah. So this shows a lack of trust of your instructor. that was a joke. Yeah. It's not, because so in calculating Q you can assume things are 0, but I see what you're saying. But you still get a finite number, right? Yeah. But it's really low. Yeah. Yes, because it's not a halogen. Okay. But it is measurable. Okay. All right, not to put too much stress on everybody, but I'm going to set a 1-minute timer, and then in 1 minute, Mean Melissa will collect the quizzes. Somebody has to be the bad guy.
I have a question. So why do we change the probability? Like we used in earlier chapters the notation being PJ. Why do we switch to pi?
PJ was for systems probability, and so basically all we've done is we've gone from capital letters to lowercase letters,
okay,
right?
Gotcha.
Does that make sense?
The
they mean the same thing. It's just that we're talking about a probability for a particle. I think it's for depression, but I'm not sure. I'd Google it. I don't know. All right, time's up. Melissa's going to be coming around, so write quickly. And I will share in the meanness. You guys done? Thank you. You guys there? Thanks. Thank you. You can't. You guys done? Yeah. All right. You need to put something down quick. Quick.
Yeah, errors.
It shouldn't, but it's all good. It's all good. Okay, you guys. Time's up. Thank you. Thank you. Oh, thanks. All right, and like I said, on the annotated posted lecture notes, the answer will be revealed. And it's a really, really, really small number. Okay, so here we're just going to do a real global summary. We've shown for a monoatomic ideal gas, that we can use our expression relating the system partition function to the particle partition function. We have derived the expression for translation. We've derived it for electronic partition function. And then we, of course, can use both of these to calculate what the energy of the system is. So again, the same thing that we've done before. Here I'm talking about the system energy, kBt squared, partial natural log of the system partition function with respect to t. So here I'm just going to plug in, this is big Q raised to the nth power over n factorial, right? We can do our little separation. That's going to pull n out in front, right? And then we know that that's going to be minus the natural log of n factorial, not a function of temperature. That goes away, so I'm left with the derivative of the natural log of the product of these two. And we know that the natural log of the product is the same as natural log of the partition function of translation plus that of electronic, all right? Right, you can take that derivative. We've done the translational one before. This is the electronic one, right? And going from here to here looks like magic, but you will show on the next homework assignment that it is not magic. All right, so from here to here, that's homework 7, number 8. All right, so you get to experience the joy of the derivation, right? And then just to reiterate, so the thing that's nice about all of this is that this first term gives us explicitly the translational energy. Of our system, or I guess should say that the portion of the system energy that is translation, and that second term is the electronic energy. And if you think about how we started everything out, this is the electronic energy above the ground state. And hopefully what we've demonstrated is that this is often going to be essentially 0. Okay? So we'll just say usually 0. Okay? All right, and then once we have an expression for the energy, we've previously shown that if I take the derivative of that energy with respect to the temperature, that gets me the heat capacity at constant volume. So for this case, that will be 3/2 NKB, right? And if that's per mole, that's Avogadro's number, and that means it's going to be 3/2 R, okay? All right, now in doing this, I've assumed that this is essentially 0, all right, because we just don't want to do that derivative, right? But we know that practically it is. So assuming E electronic equals 0, okay? Or everybody's in the ground state. Okay, we also know that we can use this equation to calculate the pressure. So we've derived this previously, the pressure of our systems, kBt, partial ln Q with respect to V. Again, we've got our system partition function. We can break that up in translation electronic. We can separate these two terms. And when we step back and look at the expression, this electronic partition function has no volume in it, right? The only place that volume shows up is in here, okay? All right, and so what we can say then is that our pressure is equal to NKB T partial ln V with respect to V plus, for completeness, partial ln. I'm just going to circle this and this. I'm going to call that Z with respect to V. And we know that that second term goes to 0, all right? We're left with NKB T, and what's the derivative of the natural log of V with respect to V? That's 1 over V. All right, and of course that's the ideal gas law, and it makes total sense that we're predicting the ideal gas law because everything has been derived for an ideal gas. Okay, all right, and then in the homework, I believe there was an assignment that showed that if you had a different partition function, you could get a different equation of state. Okay. All right. Next up, we're going to talk about the 0 points. Well, actually, overview. Energies for diatomics. So diatomic ideal gases. All right. Just a little reminder of where we start on this. When we're talking about vibrations, we've assumed that we can model this using a harmonic oscillator. And when we've been talking about rotations, we've been assuming that we can use the rigid rotor model. Okay, and then just the overview. When we want to describe the energy for a diatomic, we've got the translation, the electronic, same as monoatomics, but we now have rotational energies and vibrational energies that are permitted. Okay? All right, so again, we have the same relationship between the system partition function and the particle partition function. And we know that the particle partition function is going to be the product of the partition functions for each of the energy modes. All right, and so that in this case, what we can say is that our system partition function is going to be this portion, I'm going to say ditto, raised to the nth power over n factorial. Okay? All right. And then we're going to, again, our goal is to determine translational, rotational, electronic, vibrational expressions for diatomics. We've already alluded to the fact that translations will be the same as for monoatomic ideal gas. Right? And the electronics are going to be pretty similar, but there's a subtle difference. Right? So for rotations, vibrations, we need to define zero energy values. Right? And for rotations, if you look back to chapter 1, we know that when J is equal to 0, the rotational energy is equal to 0. Right? For vibrations, we saw that there was this thing called a 0-point energy. Right? So in that case, what we find is that E vib is equal to h nu over 2 for the ground state. Okay, and again, this is mostly review. All right. Okay, so with regards to the electronic energy, what we need to remember is that when we're talking about the intermolecular potential, the potential between the two atoms in here, what we've defined is the dissociated molecule as the zero energy state. Okay, so this is 0. That's different than what we do for monoatomics. So the dissociated molecule is 0, or the broken bond is 0. And that tells us that our ground electronic state is minus d sub E. Right? And again, we've defined that previously, right? And so what we can say for our partition function is that that's going to be given by, I'm just going to do the first couple terms. It's going to be the degeneracy of the ground state, right? Now, because this lowest energy state isn't 0, I can't just say the exponential is equal to 1. So it's going to be e to the negative of the negative dE, or plus dE over kBt. And then our lowest lying excited contribution to the partition function will be the degeneracy of the lowest lying state, e to the minus EE2 over kBt. Okay? Does that make sense? Right? And for the same reasons that we only needed to use the first few terms for atoms, we also find that molecules at room temperature are usually in the ground electronic states. Okay? All right, section 4.4. Oh, where is it? Oh, there we go. All right, so what we're going to do in this section is say at room temperature, we are going to find that most diatomics are in the ground vibrational state. Okay? All right, so what we're about to do here also dovetails nicely to one of the homework assignments that was from Math Chapter C. So hopefully we'll be able to get through this pretty quickly. All right, what did I do with that? There we go. Okay, so what we know from Chapter 1 regarding vibrational energy levels is that they are given by h nu, where nu is the fundamental frequency that we've already said earlier today we get from vibrational infrared spectroscopy, times V plus 1/2, where V is our vibrational quantum number, 0, 1, 2, etc. Okay? All right. And then just a reminder, connecting this back to the harmonic oscillator model, we know that that fundamental frequency is the same as 1 over 2 pi k over mu to the 1/2, right? And we've previously defined these. Let's just make sure that we remember what they are. What's the k refer to? Harmonic oscillator model? That's the spring or the force constant. And then mu is the reduced mass, okay? All right. So what we can do then is we can say, what's the partition function? So it's going to be the summation v equals 0 to infinity of e to the minus beta. Nothing new there. All right. So now what I'm going to do is I'm going to insert the energy levels, right? So it's going to be h nu times v plus 1/2, right? And again, from the homework, what we saw we could do is we could take this exponential and separate it out into a product of exponentials, right? And the one that's not changing is e to the minus beta h nu over 2, right? And because that's not changing, it comes out, we can pull it out in front of the summation. So then we have the summation v equals 0 to infinity e to the minus beta h nu. This is where your book gets really confusing. The nu's and v's look about the same, right? Okay? All right, and then what we remember from Math Chapter C is the geometric series, which is basically that the summation 1 plus x squared is the same as 1 over 1 minus x. Okay? And what we can say then is that we're going to let x be the same as our exponential function. So we're going to say let x equal e to the minus beta h nu. Okay? All right, I'm going to change pen color for a second just to make sure that we're clear here. So in that expression, we're going to say that's going to be 1 plus e to the minus beta h nu plus, and if I square it, it becomes e to the minus beta h nu times 2. All right, and the next one will be e to the minus beta h nu times 3. Okay? Makes sense? And again, you guys did this in the homework. Okay? All right, so this is nice because this basically says I can take this summation and replace it with 1 over 1 minus e to the minus beta h nu. Okay? And then I have to worry still about my constant in front of the series, so that's e to the minus beta h nu over 2. Okay? All right, because we've got all these variables, this is where, and actually I'm going to take a moment to just rewrite this also in terms of temperature. All right, so this is the same as e to the minus h nu over kb T, and I forgot the 2, all right, over 1 minus e to the minus h nu over kbt. Okay? All right. And then to simplify this, we're going to say, well, h nu over kb, we're going to call that the vibrational temperature. And what do you think the units are of that? Wow, silence. It's just Kelvin, right? Right? And that's what you'd expect, because that's going to replace this, all right? And then I'll just have theta over T, okay? And we expect that to be unitless. So then using this substitution, we can say that our partition function is going to be e to the minus theta vib over 2t divided by 1 minus e to the minus the vibrational temperature over T. Okay? All right. And that's where I'm going to leave it for today, leaving you out a little bit early. Say thank you. All right. All right. And that's because my 1 o'clock class, for whatever reason, I'm always more long-winded. Maybe I don't say the S word as often in there. All right. Have a nice weekend.